Well, good morning, everyone, or good afternoon, depending on where you're at. Welcome to the first installation of the Forge Modding and Simulation Forum for 2022. Happy New Year. Hopefully everyone's had a safe and enjoyable holiday season. So we get started today. What the purpose of today's forum is basically there's a number of external awarded research teams that are be kicking off and getting started right now. So we thought as a Forge modeling team, we'd take this opportunity to provide an update of most of all the work that we did through last year, through 2021, and then provide a glimpse and some insight of our highest level tasks and plans we'll be doing for 2022. So many of the people you'll see present today are part of the modeling team, and so I'll give a few pieces and parts here and there and hand it off to my colleagues. For housekeeping, everyone comes into the room muted. If you have a question, please type it into the chat. If it's timely, I'll be watching the chat to the degree that I can. If nothing else, we can either take the questions as we go or we'll hit them at the end. We'll warn everyone, this will be one of our longer forums. I think we will definitely go past the hour, I would suspect, to cover all this material. And hopefully everyone can stay for the whole time. But with that, I'm gonna get started. So brief introduction. I know many of you already know this, but I like doing these anyway in case you have any new guests with us today. Forgesight, it's being designed as an EGS laboratory, essentially to allow investigators to interactively develop and optimize EGS technologies. For people like us, for modeling and simulation specialists, these activities do require detailed earth and numerical models. The modeling simulation team, at least what we'll be doing by the Forge team, we're using a number of numerical models, and we're also trying to enable and do work with the research community. And importantly, we're trying to ensure some quantitative comparability of the results. And so we've developed some frameworks where we can hand off all these either numerical results, earth models, and be able to look at these things with version control. So I'll talk a little bit about that as well. So on the right here is shown generally where the Forge site is, here in South Central Utah, to the west of Roosevelt Hot Springs. You'll notice there's I-15. It's about 3.5-ish hours south of Salt Lake City. For reference, there's I-70. So there's the junction between I-70 and I-15. And also, so let me talk about some of the background goals and objectives. Our goal is one thing. We have to do some deterministic type models. We have to make predictions. But in the end, we're trying to use modeling to help elucidate behavior of EGS in general with a specific focus on Forge. So these objectives, what we're trying to do is one, provide a venue for easily accessing the modeling and simulation related data. We'll talk about that. Baseline the site conditions, provide some native state models, and be able to, so we can help evaluate Forge related changes to the reservoir itself. Evaluation analysis of testing connected to the site, be that flow testing, injection testing, stimulation tests, etc. We'll provide input and evaluation of reservoir development options and stimulation options, scenarios, and also be able, to the degree we can, look at uncertainty in that, be it either operational uncertainty, parameter uncertainty, geological uncertainty. And of course, provide input and evaluation of site development and operation options. Things like well locations, how they're completed, how we try to optimize heat recovery. And I'm trying to throw in some, I'd almost say in some of these cases where we can, some eye candy kind of graphics. So shown here on the right essentially is the MT data. This data was collected, processed, and modeled by Phil Wanamaker. This is, I think, one version old right now, but this is actually just plucked out of the Forge Earth model. Before I begin, I do want to give a shout out to the entire, at least the internal Forge modeling simulation team. And so I'm going to start with INL. I am, as I said, I'm Rob Podgorney. I'm with the INL. I lead the modeling team. A number of my colleagues here at INL include Jerry Liu, Lynn Munday, Chandu, Bolisetti, Sam, Hari, Ahmed, and others. I can't really cover everybody because the team changes depending on what we're doing at a given time or what the focus is. These are some of the more active members right now. Golder Associates, I'm sorry. Their main role here is fraction system analysis, characterization, doing a lot of our DFN work, and helping actually move those things, or moving those DFNs around, getting to the people that need them, and also doing some stimulation modeling. Aleta Finnila leads that team for Golder. Tom Dell weighs in from time to time. Aleta will present part of some of her work today. And I should have mentioned, for the INL team, we're mostly focused on continuum-based THMC modeling. And through today, Lynn will have a few things to say, and as so will Chandu. The Itasca team primarily focused on geomechanical evaluation and stimulation modeling. Branko Damjanac leads that team. Zarisa, Murillo, a few others as they need. Branko is with us today. He will actually talk about some of the stimulation modeling. University of Utah. These guys, depend on whoever's working on it, contribute to all areas of the modeling and simulation. The lead contributor there, at least primarily over the last few years, has been Penju Jing, doing a great job essentially across all aspects of modeling and simulation. Pranay Sai just graduated. Alex Goncharov is still there as well. And as I mentioned earlier, this is not an exclusive, exhaustive list. The team has changed. So in earlier phases of Forge, Ahmad Ghassemi was part of the modeling team from Oklahoma. He has since moved on to be coming off the team and working other parts of Forge. And that's just one example, but I definitely want to make sure his contributions were recognized. Geological overview of the site. And I know this gets covered a lot, so I'm not going to cover much at all. Basically, the main thing to say is the reservoir here shown in green is primarily, it's in tertiary granites. We essentially did some binary lumping of the geology here to either granitoid or sediments, essentially for a lot of our analyses. There's some younger rocks. I won't go into that. Importantly, some of these two photographs here are outcrops of the granitic material that are buried below the Forge site, but they're exposed in the mineral mountains off here to the east. So just some examples what these outcrops look like. We actually did some detailed fracture mapping of these outcrops, which really lended and helped constrain some of our DFN models. So I'm going to briefly talk about the Earth model updates. Hari Nupani, my colleague here at the INL, does the majority of that work. I support him in that. And all the data comes from the Forge characterization team. Largely, I would say, the Stuart Simmons, Phil Wanamaker do a good bit of that work, pressing information along. The Utah Geological Survey. I don't want to try to mention, I can't mention everyone. It's such a great team and so many people contribute to that. But those are some noteworthy examples that have contributed to this work. Before I talk about the Earth model itself, and I know I've mentioned this before, but I want to talk about the Earth model, numerical model, and the workflow. As most modelers know, this is an iterative process. So we developed the reference geologic model based on the accepted understanding at a given point in time. This, the initial Earth model for the Forge site came from lots of historical data, from confirmatory drilling. We built the Earth model from there. From that, we built essentially some native state pressure, temperature, and stress models based off that, and we calibrated it to the field data that we had. Also built a reference DFN or discrete fracture network model based off the well and outcrop data. And I would say did both deterministic and stochastic methods. And then we use those things to actually do models and do some predictions for the site. And Forge is an evolution. It's continually growing. Our learning and our understanding of the site continues to grow. So as we learn more through data collection or numerical simulations, this workflow process is repeated. So we do iterative updates of these reference models and Earth models as we go. So shown here on the right, essentially this is the top of granite surface, colored by temperature on that surface. And so what you're seeing here is mineral mountains that are cold off to the east. This hot spot here is actually the Blendale, the Roosevelt Hot Springs. There is an opal mound fault structure here. It's not identified, you can't really see it, but you can measure it on the ground. And as we move off to the right, we see with the Forge site is over here, and this gray box is one of our earlier, I believe that's the phase 2C reference or native state model domain. I'm not going to cover all of this. So basically the Earth model itself, it covers a footprint of about 14 kilometers by 18 kilometers, ranging in elevations from 2,700 meters down to negative 2,700 meters. So it's fairly large extent here in there, about 250 square kilometers. There's really robust data here. I won't go anywhere near all that. There actually are recordings. You go to the Utah Forge website, Stuart Simmons recorded a great presentation for the geology of the Forge site. And I mentioned earlier, essentially we made it bimodal here. It's lumped into granitoids in green and sedimentary or overburden on the right. So the major change here, the Earth model hasn't evolved too dramatically since phase 2. But between phase 2C and phase 3, we've got a lot more well drilling. So we got a little bit better handle on the topographic surface in and around the Forgesight itself. So that was a major update here in the Earth model recently. In order to actually use this Earth model and actually be able to share it and build it, we're using Leapfrog Geothermal and Central. We're kindly partnered with Sequent, who've actually been great partners with this. So what I'm showing here on the screen on the left essentially are the different iterations and versions of the Earth model. And if I talked about having traceability and tracking so we could see how our knowledge evolves, that's what Central has been really good for. Essentially, it's Git-like or an SVN-like repository where we can actually baseline change that branches and forks in this. So right now, as the Utah Forge team, we're on model number 90. It branches phase 3, year 3. So we actually just pushed this up the other day. Importantly, though, I know some of you have asked for access or information about the Earth model. We are starting to get those requests, and we are be able to accommodate as many teams as possible. And what we're going to be doing with that is, so well, you can't really read how it's all grayed out, but there's a branch that comes off our main Earth model right now, and actually is a branch created by Fervo. So Fervo was one of the R&D awardees. They were going to do some work in the Earth model. They created their own branch. They have access to ours as they make their changes. And if it, as those learning case increases, we can actually merge some of those changes if deemed appropriate into that master forge model itself. So if others of you, I know if people have had hinted or said they'd be asking, please do, and we can go from there. And shown here on the right actually is a picture of the Earth model itself. So this is just zoomed in, this large gray deviated well. That is well 16A7832. Some of these are the other deep monitoring wells at the site. And this is just an example of, it's a GoCAD realization of a stimulated fracture volume that essentially was modeled in Xsite, reprocessed through Fracman, and then handed off back to the Continuum team myself. We put it in here as well. The blue well is an idea. We're just looking for ways to start planning for well 16B. So that's just the potential for that. Very handy tools and been very useful for us. If you want any data for this, we do, essentially the important part is we can actually hand off structured or unstructured model data, contacts, surfaces, fracture planes, essentially do everything through an ASCII type file, CSV files primarily, and we do everything to a reference spatial dimension of UTM, zone 12 north, net 83, vertical datum of 1988. I do that for a reason, because that way, because we're working as a team amongst ourselves and with the community, not having to worry about things getting translated or mistranslated or moved out is very important. So but having said that, we do have some local coordinate models as well as the global coordinate system. But as long as if you want to do that, that's fine. Just keep track of your translation matrix. If you want any of these data, the phase 2 reference Earth model and the native state THM models are available on the Utah Forge website. There's some links here on the screen. We will be posting up the native state THM data for phase 3 revision. That's coming up soon, and new site data are continually being added. And I realize I'm getting a little bit long-winded here. I'm actually going to move this on to my colleagues here really soon. So now moving into the major modeling activities that we're going to talk about today. So the first thing we'll talk about is an update to the reference discrete fracture network that happened this past year. That'll be followed, and that'll be Aleta Finnila, followed by the native state model update that I will present. Then Branko, Damjanac will present on the stimulation modeling and planning. Lynn Munday from the INL will present on some fracture matrix modeling. And then Chandu Bolisetti, my colleague here at the INL, will also talk about some ground motion seismic wave propagation. So just to talk a little bit more about some eye candy here. So this is just actually a plot of this upper screen here is an output from essentially the workflow we created to be able to take stimulated fracture volumes from Xsite and remap them through Fracman, where we can actually be handing off 3D DFN with the stimulation-based aperture that comes from the stimulation models. So that's one of these things you're shown here. This is actually a triangulated DFN that is colored by the aperture, the cell aperture. This is an early version. I was looking at it, I was talking to some of my colleagues before we started, and I noticed there's some mesh quality issues. This is a fairly early version. It's colorful, but if you look closely, this is the one we're using. The bottom model here is actually some output from some more Xsite stimulation models. I won't steal the thunder from Branko when he goes to talk about that. But I'll move to my next slide, and I will actually hand it off to Aleta Finnila. I will drive the slides. Aleta will speak. This is somewhat of a summary of a modeling simulation forum that Aleta presented back in July. So Aleta, are you here?
Yep, I'm here.
All right, just tell me what to do and I will do it.
All right, let's go to the first slide there. All right, so I just have a few slides just to go over just very high level sort of Golder's activities on the team this last year and what we're working on right now. So we did spend a fair amount of time updating the reference discrete fracture network model, given the new data that we got from the new deep wells in the system. And I already gave a forum presentation on that in July of last year, and also then presented a paper summary of that at GRC. And those references are on this slide if you want the details. One of the main changes to the system was moving from sort of 3 natural fracture sets to 4. When we had the deviated well, we all of a sudden found this south-southwest striking vertical set really prominently highlighted in that, given the orientation of that deviated well, we could see those fractures. So the DFN, is really just trying to capture what knowledge we have of the natural fractures in that granitoid rock. And as we get new information, we update the DFN and try to make that available to the wider community. Rob, can you go to the next slide? When one of the, besides the orientation, the other sort of big effort on the DFN last year was try to get a better handle on the fracture size population. And for that work, we did some forward modeling of various potential DFNs with different fracture size populations, really looking at a power law distribution versus, say, a log normal distribution. We had a lot of evidence of fracture sizes from the mapping work that went on in the Mineral Mountains, where we could see fractures in the outcrops. But moving that, translating that to the deep Forge site, there are primary data that comes from the FMI logging that we do, where we can actually see fractures intersecting the borehole. So this work was sort of focused on looking at the statistics of the number of fracture traces in that borehole that sort of fully penetrated that borehole. So larger fractures might fully penetrate, whereas smaller fractures might only partially penetrate. Doing some forward modeling to see which fracture size populations work the best. So that the work of, that work resulted in really getting a better, higher confidence in a power law distribution. And that work was presented at ARMA this year, and the reference for that paper is also on this slide. Next slide. And then to support our team for the stimulation work we were modeling for well 16A, we provided some sort of simplified DFNs for that work, where instead of allowing fracture orientations to vary sort of widely, the fracture orientations were constrained to be matching the mean of the fracture set. So there were only 4 fracture orientations in these, what I'm calling simplified DFNs, which allows, when we pass those off to our team members who are modeling stimulation of these works, it allows them to mesh these fractures in a better manner. So we wanted to make these DFNs available to the wider community. So these are available on the GDR. And if you just do a search on the GDR for DFNs, you'll see this coming up, and it's submission 1317. And there's some information about how, what kind of files are available and how people can use them. And people are downloading these and using them as starting fracture orientations for various modeling efforts. And we had a request to get the full permeability tensor for some of those upscaled values. So that's being made available in a new submission that's pending right now on the GDR. So that'll be available if you need the full permeability tensor. that also will be added to support this data set. Okay, next slide. And then current work, as Rob alluded to, is our Fracman software works with fractures as discrete planar features. So our workflow in the team has been for the Golder team to create some starting DFN models for the reservoir. And then these get passed over to the Itasca team and University of Utah team to do some Excite modeling to actually stimulate, do some well stimulations on those fracture sets. And the output of that modeling is actually sort of point clouds of apertures and pressures. And for us to sort of take that stimulated work and pass it on again to later work, we needed to map those results back into the discrete fracture planes. So our workflow is taking that point cloud of data back into mapping them onto discrete fracture planes and then meshing them to support later work for production modeling. So that's taking up a fair amount of time. And as Rob says, getting those meshes correct with all the fracture intersections is challenging, but we're making great progress on that. And certainly once we have that workflow worked out, I think we'll be able to make some of those meshes that we use available to the wider community as well. All right, next slide. And then finally, we spend a lot of time looking at the FMI logs from the deep wells in the reservoir and hadn't spent as much time looking at other log data, including like the sonic logs. So a current effort is to take that sonic log data and to do some unsupervised machine learning on it, doing sort of cluster analysis on all the different signals we're getting, and do rock identification to have a sort of categorization of different rock types, see if we can identify sort of at that 6-inch logging interval details of the lithology and also whether there's significant open or closed fracture systems there, just to give us a little more information at that detailed scale about what we're seeing down there. So what you're seeing on this slide is sort of the FMI data on the left, where we actually see, we can see where fractures are intersecting the borehole and their orientations. We can look at fracture intensity if we look at sort of the number of fractures, the location with the depth along the well borehole is to the number of fractures. So looking at the slope of that, we can see fracture intensity, and then sort of linking that to what we can see from the sonic logs, where we've done a cluster analysis and can identify different rock types at different depths. So that's ongoing work, and that'll help refine the geologic model to perhaps highlight where we can see changes from the granitic rock we're seeing, and we're also seeing some gneissic rocks appear in the deeper levels. So pinpointing where those changes happen is sort of the effort that's going on right now. And I think that's it for me, Rob. That's the last slide.
Thank you, Lita. We did have a question come in about the permeability or the fractures sort of cemented. I answered it briefly, but I think we're going to let that go, Colin, until we get back and let the stimulation modelers, because they go through that in detail. So if you have questions after them, please bring it back up. So native state model update. This is Jerry Liu and myself here at the INL, mostly Jerry at this point, but we're working there. So if anyone recalls back from phase 2C, phase 2, we had a smaller numerical model domain, but in looking at some of the well completion options and trying to make sure we keep away from boundary effects, we actually increased the model domain for our phase 3 model, or phase 3 native state model, to be 4 kilometers by 4 kilometers and just a hair under 4 kilometers thick. Now, in earlier iterations, what I'm showing here in black, this is the phase 2C model domain. And if we wanted to look at detailed evaluations for fracture, things around the toe, we did essentially sub-model that. And so we still have that capability to do that on a structured mesh if we wanted to like carve into there and do smaller domains. But with our new iteration, we're using an unstructured, well, this shows the structured mesh. We have it both structured and unstructured. but we actually did an unstructured mesh for most of our models now. We take it all the way to the ground surface, and I'll show why here in a little bit. But this model domain is aligned with the principal stress directions. It's rotated 20 degrees to the east. Earlier, once again, the geology is binary, essentially granite or sediments. And I already mentioned we have structured and unstructured iterations of this. So just really quickly here, it's looking for our native state where we get some of our boundary conditions from. So we did a number of stress tests in a number of the different wells there. That comes from the characterization team. So shown here on the slide are the values we use for SH max, SH min. Since we go to land surface, we're taking that from topography, density, and the porosity of the fluids and topography. In most cases, for the granite, so the uniform, or for the sediments, to be honest, we're not super interested in a lot of the flow and transport there. So we do some things to get away from that. But so we're using a uniform reservoir properties within the alluvium. In the granites, we're either using uniform or essentially upscaled properties based on the DFN for bulk, permeability, and porosity. The unstructured mesh ranges anywhere from size to 40 to 80 meters in size. Okay, I see that. Thank you for that, Herb. And as I already mentioned, we rotated it 20 degrees. So I'm going to move off this slide to hide my misspelling. And so just show some results. So shown here on the left are two different plots. So the upper plot is just some DVRX stress in the model itself. So what you're seeing here, this is land surface. This is the Mag-Lee wash going through the ground surface itself. You can faintly see a small contrast in the stress. Shown on the bottom here is just native state temperature with the upper layer with the sediments removed. So you just see the top of the granite here, and this is the temperature distribution. That is actually in Kelvin. One of the code, my code, actually the Falcon code, uses Kelvin as its base temperature. But just showing some plots here on the right for some of the deeper wells, the characterization wells that we drilled for the site itself. 5632, 16A 7832, 78B 32, and 5832. These are plotted elevation against temperature, and these, it has been converted to Celsius. We do have a uniform temperature axis except for 78B, which goes to 300 instead of 250. We're pretty happy with the match. They're a little condensed. What you're not seeing we're capturing the model. So the blue line is the modeled temperature. The dots are the measured from the temperature logging at the site. And importantly, you'll see here in these upper sediments, we do see some deviation here. And this is attributed to shallow aquifer groundwater flow that we're not even attempting to try to capture here in the model. There's some interesting lateral boundary conditions flowing off of the site, but I think we're not going to put the level of effort in to try to capture those. But by and large, we're pretty happy with our capture of the thermal structure at the site, as well as the pressure and the best we can to the measured stress. One other thing I want to mention is we just started doing some of these things like looking at strain estimates, which is one of the main reasons we took the model domain to the land surface. So there's a number of or at least there is some measurement systems going in that'll be deployed through part of the stimulation activities to look at strain on ground surface or near ground surface. So we did a couple different models. Let's just looking at, we had to significantly change the permeability, but essentially this is just a continual model of the entire native state where we injected the planned volume of fluid over the same amount of time. It's in the stimulation plan, and just looked at some resulting strain at the surface. And these are just quantitative right now, but I just wanted to show that this is one of the applications for the native state model. With that, I am going to transition over and hand it over to Branko Damjanac. Branko, are you here? If you are, you might be muted. All right, sir.
Yes, I am. Okay. Thank you, Rob, and hi, everybody. So I'll present a few slides showing how we did about modeling of reservoir stimulation and some of the results. So the team that actually did this work includes Peng Sheng from University of Utah, and I tasked a team including Zorica Radakovic Guzina, Maurilio Torres, and myself. Most of these models were run actually at Idaho National Lab, High Performance Computing Center, and we actually used quite significant resources there, large number of CPU hours. Rob knows exact numbers. In certain way, it's a little bit embarrassing fact that we use that much resources, but on the other hand, it kind of makes sense considering type of the problem. Model on the scale of more than 600 meters, injection times longer than 2 hours with resolution of the order of 2 meters and explicit representation of more than 50,000 fractures. So people that you are listed here actually did this modeling, but of course the work was done in close cooperation with the rest of the Forge modeling team, particularly with Aleta, who actually provided one of the most important input parameters for the model, which is DFN. So if you can go to the next one. So we started model.
I'll interrupt for a second, Branko. So you kind of teased there for the number of CPU hours. It is somewhat embarrassing, you know. Essentially, I don't know, embarrassing, but it brings the strength that I think high performance computing can play to help elucidate some of these behaviors. So I recently transitioned to take a leadership role in our computational sciences division at INL, and such I actually had a little bit of sway in getting us some CPU hours. But I believe our team used 85 million CPU hours through 2021. You know, we're talking in the petaflops range in computational capabilities we've thrown at these problems. And I think, you know, if we didn't have those kind of resources, we would have a lot more uncertainty we'd be trying to deal with for some of these simulations. But I'll stop talking there, other than to say that I know that some folks will be some of our external awardees, if they're interested in trying to access some of these resources, we may be able to make them available to others as well. Depending on our load can't get too big in the overall scheme of use of INL's machines. But so back to you, Branko. Okay, so I'll try to kind of justify use of all of those resources by showing you results in the following slides. So we started modeling with kind of generic parametric analysis of stimulation from well 16A, and the model that we used was actually carefully calibrated using the injection test data from well 5832. But despite the fact that the model was calibrated, it definitely involves quite a bit of uncertainty because of limited time and length scale involved in this field test. So in the base case model, we basically, which was calibrated, we assumed that DFN is permeable in situ. It has only frictional strength with 37 degrees angle, and we decided to carry out these sensitivity tests for the base case of injection of the water at 20 barrels per minute for half an hour. But then the purpose of sensitivity analysis was to investigate different uncertainties with respect to DFN realization, mechanical properties, strength, hydro properties of DFN permeability. Somebody, if I hear some background noise, so if you guys maybe can mute yourself. Okay. Yep. In situ stresses, but then also the purpose of the parametric analysis was to kind of investigate and understand how the different operational parameters affect the stimulation. Specifically, you know, what is the effect of injection rate, either constant rate or variable, viscosity of the fluid and type of the fluid and so on. So if you go to the next one. So then when you complete this analysis, parametric analysis of reservoir stimulation, the question is how you then evaluate, you know, and compare these different cases. The proper and accurate way would be actually to run the production models for these different stimulation scenarios, and then look at the, you know, how much
recovery of the fluid you achieve for different cases, what is injectivity, or in other words, what is the pressure to achieve certain rates, then what is the temperature and energy that you would produce. However, and that is what is the Utah Forge team is currently working on, and running this production model takes time. So we need some easier and faster indices that could help us evaluate these different models and achieve stimulation of the reservoir. So for that we used 3 different measures. So one was what is the height of either created hydraulic fractures or stimulated DFN, which are connected to the injection well and has open more than certain threshold. So in this study, we assume that 0.2 millimeters is the threshold that indicates that the fractures have been stimulated. So this first index just tells us about the connectivity. And this is probably at this stage the most important index, because we really want to make sure that we connect the injection and production well, or that based on these modeling results and also the initial field data, microseismicity and so on, identify where can we actually or should position the production well, or how far above the 16A well. The next index is the extent and in terms of area and the height of the fractures, particularly DFN, that has undergone hydroshearing. So that would be basically the area where we would expect some irreversible permeability change. And this is the type of the stimulation that was attempted to be achieved in a number of previous EGS projects. And then finally, we also wanted to see what is the extent and the height of the hydraulic fractures that would be created during the stimulation. And on the right side, we are actually showing the results, basically the extent of the fractures with aperture greater than a threshold for 2 bounding cases. So on the top is the case where we have no DFN, and what we see there is we basically propagate elliptical fracture perpendicular to the minimum principal stress, and on the bottom is that case happens when we assume that there is no DFN, or that DFN is strong and impermeable. And on the bottom we show the results for the base case for the calibrated model, in which we assume that the DFN is in situ permeable and frictional. So the contours that you showed on the right side on the bottom are basically contours of the both hydraulic fractures and pre-existing joints with aperture greater than 0.2 millimeters. So if you go to the next slide, we show basically 2 cases again from that sensitivity analysis for the base case in terms of the DFN properties. But on the left side, we show the case in which the injection rate was 20 barrels per minute for half an hour. And on the right side, we show the results for the case where we had increased the injection rate to 40 barrels per minute. And we compare these 2 models for the states where the injected volume is the same. And again, contours that we show here are basically the fractures, apertures, again, including both hydraulic fractures and the DFN with the aperture greater than or equal to 0.2 millimeters. Just to give you this, some kind of length scale, the height. So basically, this edge here is 600 meters. And you can see that in terms of contours, there is this area which is kind of more red. So that's basically actually where the hydraulic fracture is, and injection well is roughly where I'm pointing, if you can see that. And you can see that with increasing the injection rate, the actual hydraulic fracture size increases, but then the extent of the stimulated DFN becomes smaller. Now, this is just kind of qualitative picture comparing just two cases. And if you go to the next slide, we actually try to summarize results of all models in terms of those indices that I have mentioned earlier. So here in this chart, we are showing the height of the hydraulic fracture or DFN fractures that have open, and opening means that the effective stress has become 0. And we are interested in the height again because we are interested in connectivity, or how high above the injection well we can position the production well to be sure that we will have those two wells connected. So what is the interesting here looking at these results, and it's a little bit messy and it includes a lot of information. So basically, where it's not mentioned, DFN, all these other cases are done basically for realization 1 of discrete fracture network, and DFN2 and DFN3 are basically base case with 2 different realizations of the discrete fracture network. Most of the models were done assuming that the latency in the fractures is 0. There is one case where we assume that dilation angle is 2 degrees. Then we look at, so base case is 20 barrels per minute. We look at case at lower injection rate and higher injection rate, 10 barrels per minute and 40. All cases assume that the DFN is just frictional and permeable in situ. We ran one case in which we assume that cohesion in DFN is 10 megapascal and tensile strength is 2 megapascal, and that fractures are in situ and permeable until they fail, either in a shear or in a tension. And then we look at a case of higher viscosity, and also we look at the case of the power law fluid, crosslink fluid. So what we see from these results is that the case for strong DFN actually favors hydraulic fracture propagation. So in that case, we see that the hydraulic fracture for 30 minutes of injection at 20 barrels per minute, total injected volume of 600 barrels, basically propagates 120 meters above the injection point. All other cases roughly show the height of the hydraulic fracture propagating above the injection point between 50 and 80 meters. And we can see then again that the cases with a higher injection rate and also with higher viscosity also favor propagation of hydraulic fracture compared to the basically stimulation of DFN. Now, if you go to the next slide, we can actually see then how these different cases affect the DFN. And the impact of different parameters on stimulation of DFN can be clearly seen in the chart shown on the right side, which shows the stimulated area of the fractures, pre-existing discrete fracture network fractures, as a function of injected volume of the fluid for all of these different cases. What we see that most of the cases are basically clustered together. Outlines are basically case where we have a strong DFN. So in a case of strong DFN, we saw that we propagate hydraulic fracture to largest distance, but because the DFN is strong, in this case, we are not able to stimulate DFN. Now, 2 other cases which also show not very efficient stimulation of pre-existing DFN is the case with the large fluid viscosity, and also the case with the crosslink fluid. Now, looking at those all other cases which are kind of closely clustered, the one that actually shows again the least efficient stimulation of DFN is the case with the largest injection rate, and the cases which show the best stimulation of the DFN, or the largest stimulated the area of DFN, are cases with the smaller injection rate. The chart on the left kind of shows the same results, except that instead of showing the area, we're actually showing the height. And again, for the reason, because we are interested to see the connectivity between the injection and production well by the stimulated the fractures, either by hydraulic fractures or a stimulated discrete fracture network. So if you go to the next one, so those were the results. Those are the results of this generic sensitivity study, where we basically look at the relatively short injection time, which gave us ability to run a large number of simulations. Now, the stimulation from well 16A is planned for middle of March of this year, and the stimulation will first be carried out from zone 1, which is 200 feet long open hole section at the toe of the well, and the planned pumping schedule for zone 1 includes gradually increasing injection rate with a maximum of 50 barrels per minute, and the injection at 50 barrels per minute will take place over half an hour, and then subsequently the rate will be gradually decreased. The total duration of this pumping sequence will be more than 2 hours, and the volume of injected fluid will be more than 4,000 barrels. So here we are showing results for two bounding cases in terms of what we believe that is the most important factor that will affect the response of the reservoir to fluid injection, which is strength and permeability of the DFN. So on the left side, we show what is the currently calibrated model of the DFN, assuming that the DFN is permeable and frictional. And what we see that on the left, there is basically the response of the reservoir to fluid injection is dominated by pore pressure dissipation into DFN. We do propagate hydraulic fracture, but to some limited extent. On the right side, we have other bounding case where we assume that there is no DFN, or that DFN is strong and in situ permeable. And we see that in this case, we propagate basically hydraulic fracture to, unfortunately, the length scale is not included in this chart, in these plots, but on the right side, I think the height of hydraulic fracture at the end of injection is of the order of 150 meters or more. So we are hoping that when the stimulation of well 16A from zone 1 is completed, we will know way more about what is the dominant way of response of this reservoir to fluid injection. So we are looking forward to see the microseismic data and fiber optic data, and then hopefully go back and compare the field observation with results of these models, and probably then have a chance to also recalibrate the models to the data. Okay, this is what I planned for.
Oh, you have one more slide, Branko. If you want to
Yeah.
talk.
So yeah. Okay. I'm sorry. Yeah. So I'm sorry. So yeah. So I was okay. So if you go to the previous one, so in the previous slide we were showing pore pressures and the injection pressure history, and if you go to the next one, I'm sorry. So yeah, so I kind of went ahead of myself. So again, this is showing the extent of the stimulated volume or area in these two cases. On the left side, in the case when the response of the reservoir is dominated by pore pressure dissipation into the DFN, and on the right side, in case where the basically we can assume that there's no DFN, or DFN is impermeable and so strong that it doesn't get stimulated, where in which case we just propagate kind of elliptical hydraulic fracture. And again, the scale is there. I thought, you know, we have a slide with a scale. So the hydraulic fracture propagates 160 meters above the injection point, while in the case of the stimulation of the DFN, you know, the model predicts that the height of the stimulated area is more than 340 meters above the injection point. Sorry.
Oh, you're good. Thanks, Branko.
Thank you.
I see your question, Karen. I'm going to move on. We'll try to get to it in a little bit. I'm not sure the easy way to answer that one. So I'm going to move on to talk about some of the fracture matrix modeling. So what we're trying to show here through this presentation is kind of the evolution of how the data hands off from one team member to the next. So we have native state model where we get some pressure, temperature, and stress distributions. We have a native state or a reference discrete fracture network. That fracture network was just stimulated. Now we're taking that stimulated fracture network and bringing it back to look at essentially a fluid flow, heat transport, and such through that fracture network. So Lynn, I set the stage up for you. This was a modeling simulation forum from back in, I think, October, I believe. But Lynn, do you want to take over?
Yeah, so these slides haven't changed. These are just a few of the slides from that forum. So this work hasn't changed a lot. So for more detail, you can look at that. But yeah, this work was done at INL. And also a lot of this work was also done at CSIRO in Australia by Andy Wilkins. Next. So this work, we're using the finite element modeling to develop this production kind of modeling for porous flow through the fracture network. And so all this has been developed in this this Moose framework at INL, and in particular, it's in a code for I guess thermal hydraulics modeling called Falcon. So this is the loose coupling algorithm that we've implemented in Moose and Falcon, and this has all been documented pretty well by Andy Wilkins, who did a lot of the development work for this. So that webpage gives a really good overview of what this is. Yeah.
I'm just going to say, just for clarity, for people who haven't been part of these before, Moose is an acronym for INL's Multiphysics Computational Framework. It stands for Multiphysics Object-Oriented Simulation Environment. Here at the INL, there's more, or in Idaho, there's more animals than people. So we tend to name all of our codes after some kind of animal that's native to Idaho. So that's where Moose comes from. Falcon, peregrine falcon is the state bird. So that's where Falcon comes from. I'll move on, Lynn.
Yeah, so we kind of took an approach. So Moose has a lot of these capabilities for transferring data between two meshes. And one thing we wanted to avoid with these fracture networks was having to explicitly mesh the fracture network, I guess, contiguously with the matrix. So that we don't have a meshing tool that could easily do that. So what we chose was so on the left would be a conformally meshed, tightly coupled simulation. And on the right is what we've implemented in Moose, where we can individually mesh the fracture network, which is much easier just to mesh these 2D domains with triangle elements, and then come up with some type of loose coupling strategy to transfer heat between the fracture network and the matrix material surrounding it, and run that in some type of as two separate simulations that are coupled together. So I guess the fracture network, we get that from Aleta with data that's been interpolated onto it by Branko, his group, but the Excite data. And okay, and this will be for production modeling. So I guess next. Okay, well, I guess go back, Rob. I didn't realize this was already to here. So I guess, so this loose coupling strategy that we've chosen is we we have a production, or we have an injection and production nodes on the DFN mesh, where we inject the fluid, the cold fluid into the fracture mesh. We maybe run like 4 or 5 time steps on that mesh until it's whatever the stable time stepping is on our fracture mesh. We pass that heat data, all that nodal data, to our matrix mesh, and then run the time steps on it. So this is kind of a staggered time stepping strategy. And then we interpolate that data back onto our fracture mesh and take another set of time steps. And so this is actually turns out to be pretty computationally efficient way of modeling this, because we don't have to take as many time steps on the matrix mesh as we do on the fracture mesh. So so that saves us time. A tightly coupled simulation would have to take, equal number of time steps. So that's good. Well, I'm trying to think. It's a pretty simple algorithm. It was actually pretty straightforward to implement in Moose. It didn't require us to write a lot of new code. A lot of this was just using objects that were already implemented in Moose, and maybe using them in a new way to do this kind of this multi-app coupling. So Moose has this capability to do multi-apps. It's kind of a way of having 2 separate simulation domains all within the same kind of executable. And so that's the approach that we're using, and that's pretty well explained in that write-up on that previous page. And so, yeah, so the DFN mesh, the porous flow model that we're using for this, it'll include aperture for the permeability, can include temperature for the permeability, and other physics. And then I think in the mesh right now, we're only modeling heat transfer, but we could model possibly other things like or I guess porous flow into the matrix, as well as maybe chemistry or something else. But all right, next, Rob. So Aleta gave us some pretty simple fracture networks that we could kind of test the model on, and that's what shown at the left. So we have the temperature, permeating through this fracture network, and then on the right we show, as a function of time, what the temperature is at the production point. So the injection point is shown in green. You see the fluid flow away from the green point, and then in red is the production point. And so it takes a few hours for the fluid to build up enough pressure at the production point to start start production, and then so that's what you see with the dotted lines on the right. Is you have initially the whole matrix is at 200 degrees, and then it spikes up a little bit as the pressure increases, and then the pump and then it's able to start producing flow. So we looked at this, did a kind of a refinement study, and that's what all the different lines are, to see what size of meshes we need for the matrix and in the fracture network to get the right kind of heat transfer between the two. And so depending on what kind of, if we're looking at short-term production, we need a much finer matrix mesh to get the heat transfer right than if we're looking at longer-term production. So this would be looking at how how the matrix is going to be cooled down by the flow and of the long-term efficiency of this reservoir. All right, Rob, next. So okay, yeah. So also at Idaho, also on the same team as me and Rob is Sam Dulapala, and he's going to take this model, this DFN network, and determine what would be an optimal placement of the production well site. And he would do this using some type of importance sampling and some Bayesian methods to determine that. Sam's he's on this call, so if you have want more information about that. He could give it to you. I think on the next slide, I have another, a little bit more about what this, what SOM will be doing with this model. So could you go to the next one? Yeah, so we'll sample on these fracture planes to determine where we should be, maybe the best location for the production well. So the simulations I showed, it was fixed, but we would like to be able to vary it. Yeah, so SOM's come up with a sampling strategy to sample these fracture networks, and so now we have started looking at where to place those, where to place the production well. I think that's the next slide, Rob, is some initial results that SOM has looked at. So for over 90 days, depending on where you place the production well, you get different amounts of or different cooling of the fracture fluid, and I guess the energy output. And so that's what's shown on the top left, is just a time history of all these different points that SOM has sampled, and then looking at the total energy output of those on the bottom right. And so SOM would like to use some more advanced sampling techniques, so adaptive sampling, parallel subset simulations to optimize this production location. And so you saw the DFN I was using here for the development was pretty simple. And so what we have started doing is running the actual, so Aleta has taken the aperture data from the X-site stimulation results and started mapping that back onto the real fracture networks. And so we have started to run those, and we're working debugging a little bit, but we do have some nice meshes that Aleta's given us with the proper data on them to be able to run the real fracture networks. And so one thing you can probably notice is that the real fracture networks have a lot more fractures than what I've shown here. And so we're starting to see some, maybe some problems in this loose coupling approach that we're doing. And so we need to look into some efficiencies and how we transfer that data back and forth. But we do have these simulations. They are running now, so that's promising. And so now we can start looking at, now when SOM does this sampling, we need to come up with maybe a different strategy of how we sample this much larger fracture network. Yeah, so that's about it. That's it, Rob.
Okay, thanks, Lynn. I think just to kind of really drive that point home is the end product, a lot of that work will go, and it's something we'll talk about for the this year's task, is to help provide input into the design of well 16B. Is there an optimal offset and an optimal location where we can encounter more or the most fracture rock volume? Of course, we're doing this off model results, but once we get if we can get measured fracture orientations from the stimulation itself, this analysis will be done on as best we can for the real stimulated rock volume. I'm going to transition now to Chandu Bolisetti. We're going to talk briefly about some of the ground motion simulations that kind of go hand in hand with the stimulation modeling. Chandu, are you here?
Yeah. Can you hear me?
We can hear you. Please, floor is yours. We're running a little bit late on time. I apologize to put you pressure, but you're the cleanup batter. So
I will try my best. Yeah. So thanks, Rob. So quick change of gears. So this study is mainly about safety during operations, and more than just design and operation of the EGS system. It's more about induced seismicity and how we can be safe and stuff like that. So the study actually started off with Christine Pankow and others at University of Utah doing some induced seismicity analysis for the Forgesight. As I said, the motivation is to understand what kind of seismicity will be induced with these stimulations at the Forgesight. So, which is an important safety issue. So the Utah Forge Induced Seismicity Mitigation Plan report, which is actually out there in public, it was published maybe a couple of years ago. It actually looked at all the different kinds of different sources and historic seismicity at the site, and they actually tried to determine what is the maximum seismicity scenario at the Utah, at the Forgesight. So they found that the seismicity is not, the induced seismicity is not, it's actually capped by the natural seismicity, which means that induced seismicity is not going to be more than the natural existing natural seismicity in the area. And then they also found that a deterministic maximum scenario from induced seismicity is about magnitude 4 and a 1 kilometer depth. And this is also a very conservative estimate based on some induced seismicity models that exist in the literature. So in my study, which we did at INL with, actually we did that with another postdoc who is no longer with us at INL. Unfortunately, he works for the California Department of Transportation now. So what we did here is we tried to understand this induced seismicity scenarios with a little more detail using source to site finite element simulations. So we basically, can we go to the next slide, Rob? So what we do is we have a open source seismic analysis code called Mastodon. As Rob mentioned, we like to name codes here at INL after animals, and we decided to name this after a prehistoric animal because why not? So our code is called Mastodon, and it does seismic analysis simulation. So what it does, what we can do here is we can basically simulate the fault rupture, the energy release from an earthquake, and then the waves that that energy release emits and how those waves propagate to the surface, and what these earthquake waves do to a structure. Say, we actually developed this for nuclear power plant and nuclear power plant simulations, but we have used these for dams and other applications. But here, we are trying to do this for this EGS site at Forge. We can model complex 3D soil profiles. We can model complex topographies like mountains and stuff. And a specific aspect here that we want to pay attention to is topographic effects, mainly because topographic effects are not, you cannot accurately measure topographic effects with statistical models like what we use in current seismic hazard analysis. So what we are trying to do is understand these topography effects using finite element simulations instead. So that's an example I'll show here. Can you go to the next slide, Rob? Oh, yeah. I think maybe one slide before this. Okay, actually, no, sorry. Okay, so the scenario here is there's well 16A, and the scenario here is that the stimulation of well 16A would result in a small fault rupture or a rupture in the fracture, and we idealized this fracture as basically a disk with the following rupture parameters over here, like the strike, dip, and rake. And then it's actually a disk that is 100 with a 100-meter radius. And given the shear modulus, elastic modulus of the rock over there, that would result in an earthquake that's about 0.8 in magnitude, which is a very small earthquake. It will probably be barely felt if you're over there. So we wanted to see, okay, so what kind of earthquake accelerations would this result in? And so we ran the simulation using Mastodon for this scenario. Can you go to the next slide, Rob? And then we found some peak ground accelerations. We found these peak ground accelerations in X, Y, and Z directions. So I apologize, the text here is pretty small, but I can tell you that the PGAs for where the contours are red, the PGAs are actually at 0.003 Gs. So it's 0.003 Gs, which is a very small acceleration that will barely be felt. So another interesting thing we see here is that, so on the left here, the pink region in the left is actually the mountains. It's actually the granitoid, and the yellowish, brownish region is actually alluvium. So you see that most of the accelerations are actually concentrated at the feet of the granitoid, at the feet of the mountains. And that is actually it's a demonstration of topographic effects. So these are the things that we would like to capture to understand the seismic hazard better. And this is where simulations like these finite element simulations like with Mastodon, that's where these things help. So next slide, please. So yeah, so that's what we are showing here. The it was a kind of a short study, and what we showed is that the peak accelerations are very small for these kind of induced seismicity scenarios, and B, there will be topographic effects that we can capture like with these finite element simulations that we cannot capture very accurately using statistical methods like probabilistic seismic hazard analysis. So and then here I'm showing the topographic effects that we found here. They're called basin effects, which actually result in larger accelerations near the feet of the mountains as opposed to in the mountains itself. So these can only be simulated using deterministic finite element simulations like what we have shown here, and probably not using PSHA, as I mentioned. So if we have funding available, we can actually extend this work to more accurately understand what different kind of induced seismicity scenarios can affect the Forgesight or the population in that in the surrounding. There's very little population in that region, but it's good to know what kind of spatial distribution of the acceleration we can expect from these scenarios. So that's all from me, Rob.
Thanks, Chandu. So there are a few questions over there. I think there's one for you, Chandu. And there's one about some of the microseismics, which I'm going to put a hold on. I want to just move forward. I know we're running pretty late, and I thank everyone for staying on and for your interest. So I just want to say the current status of a lot of this is the native state model. It's complete. We will be publishing that on the GDR and Utah Forge website very, very soon. So we'll be able to have essentially pressure, temperature, stress, it's structured or unstructured throughout the entire domain. The updated reference DFNs are complete and published. You can go to the GDR and find those right now. The work that Branko and team showed for well 16A, the multi-zonal stimulation modeling, that is complete. I believe all the final post-processing is now mostly complete, and we'll be able to export some of that as well. And we're actually using that to inform and provide input to the stimulation team before they get ready to go out and do those stimulations in the field. I just want to briefly go over some of the plans for years 3 and 4 for at least for internal modeling. There's a lot that's going to happen in Forge over the next 2 years, years 3 and 4 of the Forge project. We're going to stimulate the toe of 16A. That happens in a few months. We're going to conceptualize, design, plan, and drill its pair, well 16B. There'll be additional deep monitoring wells drilled. There'll likely be additional stimulations in well 16A and potentially also in 16B. There will be interwell flow testing. So the modeling tasks are going to center on informing and supporting these efforts. We're also going to be engaging with the competitively awarded R&D that's now underway to also help support these things and make sure we get everybody's results here to fully inform all the activities at Forge and also make sure we're still stay coordinated. Planning is currently underway. We are working on the SOPOs and negotiating those with DOE right now. So there's lots of things that are happening. So this is preliminary planning calendar. And this just shows highlighting on 2022, 2023. This is already off by a few months, I would say, but I just kind of pulled this down from our master planning calendar. So this had showed our planning for stimulating 16A happening in February. So we're shifting this all over by at least 1 month to the right. But you can see there's 16A stimulation, analyzing, recalibrating the models. Essentially here also then beginning to plan for well 16B and testing. That right now is happening late part of 2022. there'll be some different types of flow testing and testing between 16A and 16B, with some intermediate testing happening right here as 16B is drilled for some of this testing, but also then some larger, longer term flow tests that would happen into 2023. And then second or additional stimulations in well 16A could be happening anywhere in late 2023, even into 2024. I'll go even and past that, but I don't want to get too far. The further we get away from right now, the more uncertainty is in the planning. I'm not going to be held to any of this. This is preliminary. I just want to quantify that or qualify that. That's preliminary planning, but we are moving forward. And so these also year 3 tasks, Forge year 3, which actually starts April 1st of this year, goes April to April. We're going to update the modeling plan. I'm just going to hit these really high level because I know we're short on time. We're going to work on history matching and calibration of the stimulation models that Branko presented. So a lot of it will be done at X-Site. We're also looking at phase field and or discontinuous Galerkin methods to also try to simulate those stimulation and calibrate models. Really put a lot of work into the 16B location, trajectory, and completion, the scenario evaluations, stuff that Lynn showed, you know, what the optimal offset is for 16B, where we want to put it, what's the orientation, even looking at completion options. So we'll do all this work to provide input to the planning team for operations. And part of that is short, intermediate, and long-term simulations, evaluate and estimate the heat transfer, thermal evolution, chemical evolution. So this is like full THMC modeling through those discrete fracture networks and have it interacting with the matrix, and preparing interwell flow test plans. So that's something we're going to be getting a whole lot of input from the community as to what all data should we be collecting, how should we be instrumenting, what should we be doing to we prepare to flow fluid from one well to the next. You know, high level things like flow rates and duration, but what kind of other things like what kind of monitoring data do we want to collect? What sampling frequencies, water sample, what all are we going to need? I will be actually presenting a brief an outline of this to the to some different communities over the next month, and we will start working on that plan here very, very soon. Just kind of as a teaser to some of these things, I mentioned that I wanted to show some of this work. So on the left here are some results for some initial phase field models for fracturing, and also for some discontinuous Galerkin methods. So we are moving to have multiple ways to do some intermodel comparison of our stimulation modeling here internally, and we'll also be hoping to get some of that from external teams as well. This is just kind of a show through for the base case model from X-Site. So what you're looking at here, essentially the yellow dot was the injection point where 16A is open, and that is actually what you're showing there are the stimulated fractures that are colored by the potential aperture. So for the base case, it was actually quite extensive. The largest aperture in the middle was about, right near the well, was about a little bit of, a millimeter or 1.5 millimeters. But there's so many, we had to rescale and recolor these things to show them. But there's a lot of work that's going into these. And this is where the fluid flow, heat transport, and geochemistry will be evaluated here starting really soon. Year 4, so there's going to be so much happening in year 3 with collecting additional field data that we'll be doing a revision of the reference native state models and the Earth model early on in year 4, just for the number of wells and all this other data we're going to incorporate in that. Also included in that is an update of the reference DFN. We get a lot of UBI, FMI logs, these things actually, and we're getting close enough now where some of these things hopefully we'll be able to have a mixed deterministic stochastic model, even in areas away from where we have well control, well conformance. When we do interwell flow tests, there'll be a lot of history matching to actually do model calibration on that, to look at pressure, flow, microseismics, other things, so we can look at those things. And the old goal is to reduce uncertainty in the flow and transport related model parameters. And as I said, hydraulic stimulation, a second set of stimulations in well 16A. We will essentially, as an internal team, if external contributors come and plan stimulations, we will also, we will actually simulate their plans and compare it with the results they have before we do some stimulations in these wells, but also do some planning that the Utah Forge team is also considering and conceptualizing. I think that does get me to where we're at. I know we have some questions. I know we've been here a long time. I'm happy to stay on as long as anybody has questions. Before I close though, start taking questions, I do want to acknowledgement that this funding is coming from the DOE. We're also getting Geothermal Technologies Office. We're getting additional support from the Utah School and Institutional Trust lands at SITLA. Beaver County, Utah, Governor's Office of Energy Development, and Smithfield Foods, which is a major landowner in the area, and Sequent Limited for the use of Leapfrog and Central. So I'll close there. I don't see many more questions being typed in. Chandu, if you're still here, if you want to try to respond to Roland's question or speak to it, why don't you do that? And then Karen, I'll try to come back to your question.
Yeah, I tried to address that question in the chat. I think, well, I can just summarize again, Roland. I think it's the question was, why do the PGA anomalies show narrow stripes in the north-south direction in the contours that I showed? I think that's another manifestation of topographic effects. Those contours are actually, those narrow stripes are actually parallel to the mountains on the east. And I think it's mainly actually the surface waves contributing to the peak acceleration over there. So yeah, it's in short, it's another manifestation of topographic effects. I hope that helps.
Thanks, Chandu. Scrolling through here. So Karen, I'm coming back to your question. The question was, besides microseismic, is there any other diagnostic that will be done to measure fracture height? I'd have to turn that back over to the reservoir engineering team. I don't know the answer to that. I don't know if anyone is on the call, whether it's say John McLennan or Stuart or maybe Joe Moore is on to help answer that question. But I'll take that one and pass back to the team and try to get you an answer to that, Karen, and we can go from there.
Okay, it just seems like that's a critical parameter.
Well, there's it definitely is. You know, and one of my concerns is, you know, not only, you know, where we think we may see some potential fracture aperture growth. You know, we did that 0.2 millimeter micron cutoff. You know, but does that, you know, if we see those microseismic, does that correspond to a true hydraulic impact? So, you know, Branko alluded to that. Is now we could, you know, the stimulation modeling shows where we think that the DFN or the fractures can be impacted, but unless we have, you know, but is that truly hydraulic, and how that would contribute to the overall thermal recovery evolution, I think is a critical thing. And that's something I really want to try to get some diagnostic information on once we get the first completion, and once we get 16B in there, is we get some, try to get that confirmation.
But Rob, shouldn't there be fiber optic cables in all of these observation wells?
So the plan is in 16B, I believe right now, to have a fiber optic going the entire length of the lateral. But I will say that if we've had trouble with completing and having fiber optics survive. So we can do fiber optics inside the well and have it removable. But the plan is to have it outside the well. Many of these other seismic and monitoring wells do have fiber optics in them already as well. So yes, and we will actually ways to get strain, other things along those wells. So we could actually get other things in there. But at the time that 16A is stimulated, all we're going to have is microseismic, or, you know, in seismic monitoring, other than pressure diagnostics in the well.
Yeah, and if your wells are angled and you have fiber in them, that won't give you a height, right? It won't give you a vertical height.
You know, you could be, you're likely right, and I don't. So I would say just there's a line of demarcation between the how the modeling. So the seismic team, they've been doing their own seismic modeling for seismic for essentially for designing the monitoring system. They work, you know, with the seismic hazards team. That's essentially, you know, the modeling team per se, like the group that talks here, is more interested in reservoir engineering, heat flow, fluid transport, heat recovery, well engineering. So,
and what is the fracture orientation? Do y'all have that figured out?
I'm not sure of your question. Well, we identified 4 major natural fracture sets. That's what Lita went over early on. Is that what you're alluding to?
No, I was thinking hydraulic orientation.
Well, I mean, it's defined by orientation of principal stresses. So I think, yeah, we're fairly confident about that.
Moving on, I see a question from Kevin. The question is, will a different chemical tracer be added to each fracture stages in 16A, so tracer be detected in drilling 16B. There are plans in the stimulation plan. I'm not 100% sure what tracers will be added. I know there's some talk of doing even some micro proppant injections to look for those. The trick will be trying to actually find them. So yeah, yes, that is part of the plan. I don't know the details, but we can get that back out to everyone. Is that plan has been finalized and approved. I just don't know the details myself.
So Rob, this is Kevin. I'll make one comment if I can.
Yeah.
So that was more of an answer to Karen's question about hydraulic fracture height determination. Those tracers will be added, and they're different chemical tracers that are added to each stage of the stimulation. And at least those tracers will be detectable from the returns when drilling well 16B. So that'll give at least some confirmation of hydraulic fracture height achieved, because that tracer could have only come from the injection on 16A.
Thanks, Kevin. Other questions, comments? And if anyone's shy and do not want to post a question here, but you have some feedback, even if it is critical, please send it. I'm going to type my email address in the chat here. And I take any feedback, good, positive, negative. Snide remarks are welcome. We'll move along. Our goal is to just do the best job we can and have the most success possible for the site. So I think I think we're lacking. All input is welcome. Last chance for questions. Well, I thank everyone. I will be working on a schedule for the rest of the year, whether we bi-monthly or monthly. I am not certain yet. So be looking, we'll send some announcements out through the Forge communication channels once we get the 2022 forum schedule plan and get our speakers aligned. So we'll be looking for that, and hopefully we'll talk to everyone soon. Have a great rest of your day. Thank you.
Thank you.